Testing, testing. 1, 2, 3. Testing, testing. Testing. Very good. That works. Okay. Let's just see if we got this going. And I need to post a link. Share, copy. And go to our course. Hello. Come sign in and grab some snacks. Sign in and grab some snacks. All right. All right, we'll just do a quick check. I think I got it all set up. And if you guys are ready, we're going to get started. Let's see. Sound check, sound check. Excuse me, I'm going to be sniffling, maybe coughing. But I'm feeling much better. Hopefully you guys are feeling good. Everybody feeling good? Woo! Sunday afternoon. Just washed my car. Woo. I know. Washed my wife's car too. I know. Sound check. Sound check. Whoa. Sound check. Whoa. Okay, it works. That's wild. Infinity, right? Okay. To infinity and beyond. Okay. So some people might be here to get the most the preview questions. I'd rather not give you those preview questions. So we still have 4 days to go to the tutors. So if you are here today, I will go over them after the review is done if you're interested. But otherwise, please go to visit the tutors. They want to see you. So if I give you the questions, many of you might not go. So please go to the tutors. Those of you here, I will do them, but after the review is finished, and I will shut the live stream down. Okay? Any questions? Got that? All right. So let's go ahead and get started. So exam 3 is coming up Thursday. Did it work? Let's see. That's what you have to do. I need to Mac more. Okay. Mackle more. No. Okay. That's not what I said. That's what I said. Okay. By the way, actually something has just changed. A student notified me that NASA has now named Ultima Thule to be something else. Anybody know the name? Akaroth. But I think I'll leave it for now because it just changed. So it's a little bit late, right? Okay, so take a look. Starting up, I'm going to start at the beginning. Is that okay? Everybody good with that? I'll go through the entire thing. Okay, so starting off, just a little tiny little piece of the Kuiper Belt object, Pluto. Pluto is a Kuiper Belt object, also called a dwarf planet. And you know why it's a dwarf planet, perhaps? But one of the major discoveries made by the New Horizons mission. So what were a few of the things that we saw? And now, what do we think about Pluto? Is it a dead, boring world, or is it kind of interesting? And the answer is it's really interesting. And they're actually talking about another mission already to go out there. So what was really amazing was we found a living planet with mountain ranges and smooth areas and rough areas and lots of interesting stuff. The largest glacier in the solar system, made of nitrogen ice. And then we also discovered some pretty cool stuff about the moon. Charon and Pluto are both covered with a red dust, which is an organic compound, and blah 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 blah. Let's see what else. So Pluto is a Kuiper Belt object. It's a dwarf planet. Why is it a dwarf planet? I think you guys know why, right? Does it orbit the sun? Of course. Is it round? Yes. But has it swept out its orbital path of debris? No. So it's a dwarf planet. And Charon is a really big moon compared to Pluto. Pluto's is smaller than our moon, right? So it's smaller than our moon, and Charon is about half of its size. So Charon is tidally locked to Pluto, right? The orbital period matches the rotation period. But Pluto is also locked to Charon. So the two are orbiting each other and facing each other all the time. That's kind of unusual. We've never seen that before. So we do expect to see it the longer you wait, the longer system evolves. Okay, and then after Pluto, New Horizons flew past Pluto. Why did it fly by? Why didn't it go into orbit? Anybody remember? It was going too fast. It couldn't slow down. It was going too fast to slow down. And so it shot on, and actually there's enough fuel to go to another mission. They went to Ultima Thule, which is a two-lobed thing, almost like a comet, actually very icy object. It's kind of flat, which is a little funny. We didn't talk too much about it. But what else? And then they're actually they set their sights on they're gonna be a third mission as well. So we don't know what it is yet. They don't know what it is yet. They have to wait until the position of the sun is better so that they can look out at Pluto and find a good candidate. So anyways, and yeah, the real name is Akaroth. Forget it. Don't worry about it. You don't have to know it. Everybody signed in, right? And grab some cookies so you can get rid of them so I don't have them in my office. Okay, so that's about it. Okay, so what are the mountains made on Pluto? I guess that's one of the things you should know. Mountains made of water ice, kind of like the planet Titan, right? That was actually very similar. We don't have any liquids, though. There's no liquids on the surface. There's a little atmosphere of nitrogen. And like I said, there's some organic compounds. Pluto is kind of like a comet. When it comes close to the sun, it has more atmosphere. And further from the sun, less atmosphere. Okay, that's about it. Moving right along. Okay, so our chapter 10, the sun, the closest star, right? So you're supposed to know a bunch about the sun, including the word plasma. Why is the word plasma up there? Because what is the sun made of? Plasma, okay, versus gas. What does gas imply? A neutral atom where the electrons are together with the protons, neutral atoms. In fact, they're ripped apart. Most of them are ripped apart. The electrons are free, which means that the interior of the sun is made of material that's really charged up. So it's bouncing around not only from high energy charge, but from electric repulsion. So it's a pretty big deal. Hey, Nana. Okay, so you're supposed to know that fusion, nuclear fusion, is the process that keeps the star alive, right? And a star that is burning or fusing hydrogen in its core is called a main sequence star. Every star begins as a main sequence star. And then they evolve from there, right? So every star begins by fusing hydrogen in the core. The hydrogen turns into helium. Yeah, help me if you can. Make sure that I hear that you guys know something, right? Okay, that'd be great. Okay, so now, as long as the star is alive, what force is pulling in on the star? The force of gravity. And which force is pushing out against gravity? The radiation pressure. That's the word, right? So the name of the force is radiation pressure pushing out. We'll talk about where that comes from in just a moment. But it's important to know that which one is bigger? Trick question, right? Which one is bigger? Neither one. They're the same. It's called hydrostatic equilibrium. The force of gravity is exactly balanced by the radiation pressure. Is that always true? No, right? Later on, as the star evolves, we'll see that one gets bigger than the other, and then things will change. But it always will try to establish equilibrium. So how does the star establish equilibrium? The force pulling in, gravity, is balanced by the push of radiation pressure out. Okay? The star will live that way for quite a while before it does any changes. Okay, so radiation pressure, why don't we talk about that right now? How do you get radiation pressure? What's generating radiation pressure? So in the core, we have what process taking place? Nuclear fusion. Make sure you say fusion. What's the other word that's not happening? fission. Fission is not happening. That's happening in the Earth when atoms break apart. That's called nuclear fission. But in the sun, nuclear fusion. Atoms are joining together to build larger atoms. One of the byproducts, well, besides the energy that gets released, one of the byproducts is high energy photons called highest energy photons called, okay, we're blanking, gamma rays, okay, highest energy that you can get of light. And those do not come out of the sun, right? They never get out of the sun because they are absorbed in the zone right around the core. They're absorbed and then recreated as a lower energy photon, and then absorbed and recreated as a lower energy photon. Continue to do this, and the energy of that original photon doesn't escape for 100,000 years, right? So it's the bouncing around of all these photons in the radiative zone that generates radiation pressure, right? That's where you get it. The photons can't get out. That's where the pressure is being generated. Outside the radiative zone, we have, I'm jumping a little bit out of order, but outside of the radiative zone, we have the convective zone, okay? So the sun is not a solid object like the Earth is a solid on the surface, right? As a result of that, the rotation rate is not one number, right? The sun rotates at different rates. The equator is the fastest, 25 days, and the poles are the slowest, about 35 days. And because of that, we know that the layers of the sun get tangled up. And we'll talk about that later, but the magnetic field is part of that story. Okay, so I guess I'm going to go through it one more time. The core, the innermost piece, right? We got this picture in your brain. The core, right, where the fusion happens. It's only in the core that it's hot enough for fusion to happen. Why is it hottest in the core? What makes it hottest in the core? It's the deepest part of the star, right? So it's the densest and the highest pressures are there. So it's the densest and highest temperatures in the core. Outside the core, we have the radiative zone, where radiation is the dominant mechanism for energy. And it gets trapped there, which is making the radiation pressure. Outside that, the sun goes to the most efficient mechanism it can find, which is convection, which means hot plasma rises and cold plasma falls, right? And so that carrying of energy is called convection. The outer layer of the sun that we can see is called the photosphere. It means literally the light sphere. And just outside that, the atmosphere of the sun is a pinkish layer because of the hydrogen, which emits a red color, called the chromosphere. And outside of that is an almost invisible layer of very high temperature plasma called the corona. It's actually about 1,000,000 Kelvin. We'll come back to that in just a second. Okay, so we're mentioning the strong nuclear force. Why do we want to mention that? I feel like that's worth a review. So let me just go ahead and jump over to the board. The question is, why do protons not normally want to get together? Why do protons not normally want to get together? They have positive charge, right? So two positive charges don't want to get together. They repel each other. What force causes them to repel each other? What's the force called? The electromagnetic force, okay? They repel each other. So they're being pushed away. How do you force them to go together? By giving them enough speed, right? So speed comes from the temperature, right? So the higher the temperature, the faster the speed will be. You need about 10 million Kelvin to get the high enough speed so that when they slam together with this velocity, they can be right next to each other. They never actually make contact, but they get close enough so that a new force can step in. And this new force is stronger than the repulsive force and actually glues them together so that now they form a nucleus. So this force which holds them together is the strong nuclear force. Pretty cool thing, right? All right, so we got gravity, very weak, electricity, pretty strong, not as big a range, and the strong nuclear force, very strong, but incredibly small range, right? It only works in the size of a nucleus, right? Not outside of that. You guys like my voice? I'm not sure how I feel about my voice. It's kind of gravelly. Like if I were Dragging my knee on it would hurt. Okay. Any skateboarders here? Know what I'm talking about, right? Road rash? Okay, never mind. Not relevant. Okay. Just trying to have fun. Okay, so the mechanism by which nuclear fusion is happening in the sun is called the proton-proton chain. Let's go ahead and quickly review that just so you can see. That's kind of a big deal. Actually, you know what? It's on Wikipedia. I stole it from there. PP chain. Wikipedia, the best encyclopedia on earth. Thank you. Oh, it's sideways. Okay, well, whatever. It's okay. All right, take a look at that. This diagram will start at the top this way, right? How many hydrogens go in at the top? 4 go in, and down at the bottom, 1 comes out. Now, what I didn't tell you is that 2 more hydrogens go in, and then 2 more pop out. So if we ignore those, the net result is 4 hydrogen go in, and 1 nucleus of helium comes out. So 4 hydrogen nuclei gives you 1 helium nuclei. And this is called the PP process. So it's one of the mechanisms by which fusion can happen. What's the other mechanism called? The CNO, right? We'll look at that in just a second. But this is the dominant mechanism for smaller size stars. If your mass is less than 1.3 solar masses, this is how you get most of your energy. How do you get your energy, though? What's the mechanism for getting energy? So the answer is, if you measure the mass of the hydrogen and the helium, do they weigh the same? Is the mass the same? Which one is greater? The hydrogen you put in is more mass than the helium you get out. Some of the mass is destroyed, but it's not gone, right? It's turned into another form of energy. According to the formula, E equals mc squared, right? That's the reason the sun is working. So either way, whenever you are doing nuclear fusion, if the product you get is less mass than what you put in, then that energy can be released. And that happens all the way up to the fusion of iron. So up to iron, stars can get energy out of nuclear fusion. And remember, at the end, if you have iron and you try to fuse it, it doesn't give you energy, it takes away energy. So we'll talk about that again. Okay, so PP is the one, and then what's the other one called? I said CNO, okay, CNO. Pretty picture. Okay, it's a little more complicated looking, but again, don't worry about the complicated. Just try to start with the elegant, beautiful part, which is you start at C. You start at C. I have no laser. 1 second, let me get my laser. Or you at home have to me snorting. All right. For the people at home, they get to hear me sniffling. Okay, sorry about that. All right, here we go. Take a look. Here's the C that starts to cycle off. 1 hydrogen comes in, and then stuff happens. A second hydrogen comes in, stuff happens. A third hydrogen comes in, stuff happens. A 4th hydrogen comes in, and the helium breaks away. Okay, so what's the net result? 4 hydrogen, 1 helium. Same basic thing. Jay, if you want to come sign in and get some snacks, help yourself. Okay, so anyways, it's the same process or same outcome, but what about this process is different than PP? Anybody? Remember what it is? More efficient, right? It's faster. So it turns out it's a catalytic process, which means that the carbon, nitrogen, oxygen are used to make the reaction occur at a faster rate without actually going into the reaction and getting used up. So we end up producing this at a faster rate. So what kind of stars are doing this one predominantly? Larger mass stars. And that's why they're able to produce more energy because they're doing a more efficient mechanism. All right. Doesn't remember. Come on, Mac. You should remember. Okay, proton, CNO. All right, what about antimatter? What's antimatter? What is the matter? Okay, antimatter is not normal matter. It is anti, right? Antimatter. So antimatter, you're supposed to remember the standard model. Again, you don't have to know everything in there. It's not on the list. But you need to know that antimatter is real. It's not an imaginary thing. And certain forms of antimatter you should be aware of. For example, the positron. What is the positron? It is an antimatter electron, antimatter electron. The positron is a positively charged particle of antimatter. And what happens if a positron meets an electron? The word is, I have it down here, annihilation, right? They're gone. The two particles are gone. One particle of matter, one particle of antimatter. It turns out either way, energy is just is energy, right? Matter is energy, antimatter is energy, and energy is energy, of course. It turns out that if you have energy, particles can just spontaneously come out of nothing, right? Out of energy. One particle of matter and one particle of antimatter. This is happening in the sun as well. We don't worry about it so much, but it is happening. It's why the reaction happens the way that it does. Okay, so what you really need to know is the positron is one of the byproducts of nuclear fusion, and they are going to be annihilated by any electrons they find, okay? And then leaving nothing but pure energy. Okay, that's what you need to know. Positron, antimatter, okay, what would be, yeah, that's it, never mind. Okay, neutrino is another byproduct. What's a neutrino? It is a very tiny little particle, very tiny little mass that seems to not interact with matter. And so one of the crazy things about neutrinos is that they shoot right out of the sun without stopping. Unlike the photons, which couldn't get out, neutrinos just fly straight out of the sun. I feel like I should just show you that picture so that you can see that picture again. It's pretty relevant. Chapter 10. The picture you want to understand is that photons bounce around, but neutrino shoots right out. It's highly likely that this picture will be on your test, because it is. Okay, so here is a picture. So you need to know what this picture is trying to show you, right? This is a picture of the sun, but there are straight lines and there are the little tiny straight lines that are bouncing around inside of the sun. So these arrows that are shooting right out are the neutrinos, right? So the sun is shining with light, with heat, well, that's light too, and also with neutrino flux. This neutrinos hit the Earth, by the way, and most of them go right through the Earth. They're going through us right now, right? We don't feel them, nothing happens, we're fine. Although maybe once in a while they do, but it's so rare that you maybe not even in your lifetime, right? So that doesn't mean it doesn't happen to you. But they do actually sometimes interact. We have detectors around the world to try to catch them. And I haven't told you yet, maybe today I will tell you that in the past we have detected some neutrinos, and that's kind of an exciting thing. But they shoot right out, and the light takes a very, very long time to get out. Okay, so neutrinos, small mass, they don't interact with matter. They're strange. They're really weird. So they're exotic. That's about it. That's all you really need to know right now. Okay, they're exotic.
So for that image, you just need to know that they shoot out?
They shoot straight out without stopping. That's the main thing, yeah. Okay. And they're a byproduct of the fusion, right? They're one of the things that shoot out, that come out of the fusion. Okay, solar granulation. Again, I should probably just bring up a picture, huh? Solar granulation probably helps to look at a picture. The picture is right there. Granulations are the concept that the heat energy flowing out of the sun in the outer layer, called the convective layer, is rising in the middle and falling on the edge. The way we know that is that the middle is brighter and the edges are dark, right? So brighter on the sun means hotter and darker means cooler, right? That's the key idea. And it turns out that works with sunspots as well. Oh, I like that. That's what I should do. Okay. Maunder minimum. Okay. I mean, every one of these is a picture, so I should just show you the picture, huh? Is this helpful or no? That's a sunspot picture, right? What's the center of a sunspot called? The umbra. And the area which is not quite as dark is called the penumbra, right? And again, why are they darker? Because they're cooler. Same principle. Darker means cooler. Okay, here is a picture of sunspot activity since 1630, 1610, no, sorry, 1610, something like that. And if you notice that there's sunspot activity that's pretty regular, not the same number every time, but the peaks seem to be about 11 years apart. You're supposed to know that. The sunspot activity is an 11-year cycle. But there was a period of time when there were no sunspots. And it wasn't because nobody was looking. People were looking and there were no sunspots. Why? We don't know. We have no idea right now. But it might be a pattern that we will come to understand later, right? Yes, question. Yeah, almost 60 years actually, right? 60 years without sunspots when they were seeing sunspot activity. Now you'll notice that we only saw a few cycles before that, but actually since then we've seen very repeated 11-year cycles, right? It's really quite good. Okay, so 11-year cycle, we'll come back to that too. Oh yay, I didn't forget. Okay, so there's, again, words. So we have sunspot, prominence, flare, coronal mass ejection. Those are words that you're supposed to recognize. So a prominence has a feature. Again, if I show you a picture, the idea is that, that didn't work. That didn't work. I don't know why that didn't work. Was doing so great. Almost thought I was macking. Okay, so the key thing, the prominence, I don't know if you can see that picture, is that the loop of material comes out of the sun and back into the sun, right? So that's actually a sunspot, a pair of sunspots, right? So a pair of sunspots have formed here on the sun. So a pair of sunspots have formed, and we are seeing a prominence linking from one side to the other. By the way, we might as well mention right now that sunspots are magnetic. So one spot is a north magnetic pole and the other is a south magnetic pole, okay? This loop is following the magnetic field lines, which we'll talk about in just a minute. Any questions? That's called a prominence. A flare is one where the prominence has twisted and pinched off, and it looks like a single piece shooting away. So single polar flare. Here we go. I don't really like their pictures all that much. That's a prominence. That's a prominence. That's a pretty good flare. You see how there's just a single feature? Doesn't look like it's coming back to the sun very much. And the reason is part of the magnetic field has pinched off and is now moving away from the Earth to make an enhanced solar wind, actually. So there's more solar wind as a result of that. And then the last one that you have to know about, which I think the book slide is pretty good, it's called the coronal mass ejection. Here is a coronal mass ejection. So coronal mass ejection are enormous outputs that are actually have a chance to really cause harm if we got hit directly by one, but they don't hit us very often, right? Space is huge, so the odds are very small that they're going to actually go in the direction of the Earth. Not only that, but it turns out the biggest ones are near the poles of the sun, which means they can't point at the Earth at all. So that's actually one of the reasons why we haven't been hit very often. Okay, so these don't happen as often around the equator, which is where we would be located. All right, so let's back to the study guide. I like to do that. Okay. So solar max is the idea. I think I need to talk about, I'll come back down here. Solar max is the idea that there's a maximum number of sunspots. At the peak of the sunspot activity is when the sun reverses its polarity. So that happens every 11 years. The sun reverses its polarity. So if north is on top at 11-year mark, south is going to be on the top. 11 years later, north will be back on top again. So the sunspot cycle is 11 years, but the magnetic cycle is 22 years, right? Two of those sunspot activities. A coronal hole is one of the areas where we see the corona seems to be weaker, and we get more solar wind coming out of that. It also seems to be an indicator that a coronal mass ejection is going to happen. And heliosphere is the bubble around the sun from the magnetosphere of the sun, the most powerful magnetic field in our solar system. And the heliopause is that area just outside that. So you're outside of the solar system, you're actually in interstellar space at that point. Okay, so I'm going to jump down now to the be able to. So let's see. There's a lot of interesting things here. Okay, so describe each layer of the sun, the core, where the energy is being made, the radiative zone, where radiation is trying to escape but cannot. It's primarily radiation, right? At the top of that zone, you have convective activity, the convective zone. And finally, you get to the surface, the photosphere. Now your radiation is the key thing, right? You're radiating light away from the sun. Okay, PP and CNO, I think we kind of did that already, right? We talked about they're basically the same outcome. 4 hydrogen go in, 1 helium comes out, but the CNO is more efficient in larger mass stars and therefore is the dominant mechanism. Let's see, why are elements below 26 release energy and why does element 26 not? What's special about element 26? I actually didn't go over this, so I think maybe I should throw that up real quickly, right? The slide that you're thinking of, darn it, I should have just alt-tabbed that. Oh well. We're trying to remember this slide here. This slide here of the efficiency of the nuclei. It's called the binding energy per nucleon. And something special about Fe, iron, it is the most efficient nucleus, right? So if you wanna become more efficient, you wanna be like iron. And so if you're a small atom, how do you become like iron? By doing nuclear fusion. So they're going to build up larger nuclei, which become more efficient, therefore releasing energy. If you're a large atom, the way to become more efficient is by splitting apart. So anything over here does nuclear fission in order to release energy. If you force this to do fusion, then you get something less efficient, which means that you need to absorb energy from the environment, which means the star is going to die. Right? So when we talk about stars using iron as a fuel, they're about to die, right? A fraction of a second away from dying. So iron is the most efficient element. Somebody remind me to just alt-tab that. Okay. Okay. Okay, so let's see. Explain how each stage of its life a star establishes hydrostatic equilibrium. I guess the question is, what if the forces are, what are the 2 forces called that establish hydrostatic equilibrium? Gravity and radiation and pressure. So we can ask the question, which one is bigger? Let's say that one is bigger, right? Let's say that gravity is bigger than the radiation pressure. What will happen to the star? It will shrink, right? As it shrinks, what happens to the temperature inside? It gets hotter, which means what? The radiation pressure builds up, which means eventually it can stop, right? And the star continues to live. What if the radiation pressure is larger than gravity? What will happen? It will expand, right? But as it expands, what happens to the internal temperature? It cools down, and therefore it establishes a new equilibrium, which is larger, right? So the star can grow or shrink depending on if the forces are not balanced, but it always does it until it reaches equilibrium again, and then it stops. Okay, so blah, blah, blah. What happens when matter meets antimatter? Annihilation. That's the word, annihilation. What's convective flow, right? Where's the flow? The upward flow is happening in the middle and the downward flow at the edges, right? How does the sunspot form and disappear? Okay, so this is a big deal. This is actually, even though I only wrote it in a couple words, it's actually a key idea. And I talked about it in class as have something to do with the pressure coming from the magnetic field. So sunspots are magnetic, and they form when a piece of magnetic field pops out of the sun that wasn't there before. And so you disturb the equilibrium, and what happens is the extra pressure makes it grow, right? So should we run through that? Or everybody, how many people just feel like they got that pretty well? Feel pretty good? Anybody want to review it? Okay, a couple people, all right. So let's review that. Slide right over then. Let's make a sunspot, okay? So I better turn the light back on. Yes. Over here in Kelly Studios. I should do a sound check once in a while, huh? Sound check, check, check. Anybody at home? Tell us. Nobody's watching. Oh yeah, I liked your skateboarding joke. Thanks. That's funny.
How many views are we talking?
Huh?
How many views are we talking?
I don't know. Liz, hey, you can hear me. Okay, good. Thank you. Actually, that worked. All right. Thank you guys for responding. That's wonderful. Okay, so let's make a sunspot. And the way the sunspot works is I'm going to describe the effects. So there's going to be the surface of the sun, and we're going to have a place where a spot is going to form, right? Where's the spot going to form? It's going to form where the magnetic field has popped out of the sun. Okay, so what we want to talk about is how does it grow, what makes it grow, and why does it shrink again when it's done? Okay, so we're going to go ahead and take that spot and make a little quick story. And I'm going to tell you that there's a temperature inside the spot and a temperature outside the spot. And before the spot does anything, what can you say about the two temperatures? They're the same. There's no spot there, right? So before the spot, the T inside is T outside. In fact, this boundary is just kind of artificial. I just made it up. Okay. Now, the reality is that the temperature is actually going to create a kind of pressure called thermal pressure. Thermal pressure is the speed of the plasma moving around, bouncing off of itself. And so there's going to be thermal pressure. We're going to go ahead and put thermal. We're almost done. It's just a few seconds more. Thermal pressure, we're going to have the pressure inside, right, because of the temperature. And of course, because the temperatures are the same, it's going to match the outside pressure as well. Nothing's happening, right? That's not interesting. As soon as the spot forms, inside, we are now going to have a new kind of pressure. And I'm going to call that magnetic pressure. So the magnetic pressure wasn't there before, magnetic pressure. Called PM, right? We're going to add to which side? Well, the inside, right? So we're going to add to this side, which means that they are no longer going to be equal. Which side is bigger? We just added something that wasn't there before, so this side is bigger. What happens to the spot when the pressure inside is bigger than the pressure outside? It grows, right? So it begins to grow, right? Expands and grows. And why does it stop? Well, what's happening to the temperature inside at this point? Because it's expanding, the temperature goes down, which means that the thermal pressure is going down, and eventually you're going to reach a new equilibrium. So the new equilibrium is going to be when the pressure from the thermal pressure inside plus the magnetic pressure are exactly enough to balance the pressure from the thermal pressure outside. Then it'll stop. So what do you get? You get a dark colored spot because it's a little bit cooler than it was just a few minutes ago. Well, a day ago or whatever. Okay, a little while ago. And so that spot will exist as long as this balance remains. Now, at some point, the magnetic field just goes away. So as soon as you take this away, what's going to happen? Will it be in balance anymore? And here, because it's not in balance, you just took something away that was in balance. In fact, now this one is less than this one. What will happen to the spot? It'll shrink back down again. And what happens to the temperature inside as it shrinks? It heats back up again. When will it stop? When it gets back to the same temperature as the outside temperature. And so the spot will go away. All right? That review help you guys? You're good? Okay. So sunspots form and then disappear, all based on the magnetic field and the pressure that that magnetic field exerts. Okay, so magnetic pressure. Yeah, let me know if you don't hear me at some point. Gang at home? Okay. Let's see. So why is the sunspot cooler than the surrounding? I just gave that up, right? Tell me why. Why is it cooler? Because it is expanded and in the process got cooler. Okay, that was easy. How do sunspots form? From the tangling of the sun's magnetic field. So we didn't quite describe that, but what's happening? The magnetic field, when the pole reversal happens, it's very smooth. That's not true. Actually messy, I'm wrong. Other way around. When there's no sunspots, that's what you want to say. When there's no sunspots, the magnetic field is very clean. That's what I want to say, okay? But what happens is, as the sun differential rotation takes those magnetic field lines, it'll start to twist them up, kind of like a rubber band. That's the analogy we use. And so after a while, as you wind it up, it bunches up. And we think that that's the reason why the magnetic field pops out of the sun. So then a sunspot is going to be there. It'll go away after a little while. The sun rearranges itself by flipping its polarity, and then it goes back to being kind of quiet again for a while. But it's actually at the peak of activity. So there's a lot of sunspots when it's flipping. So that's not quite right. So when there's no sunspots is when the magnetic field is the smoothest. Okay, I just described that. Okay, magnetic field is smooth. The magnetic field is smooth, no sunspots. Magnetic field is tangled and twisted, lots of sunspots. Okay, memorize the sun's life. Okay, it begins as a protostar, probably a few million years, something like that. Main sequence life, how long? 10 billion years. Red giant star, 1 billion years, and then white dwarf after that for the rest of its life, okay? What's the period of rotation? Okay, I put 34. Maybe that is the right number. I'm not that worried. 25 to 35 or 25 to 34, or something like that. And the length of time for a photon to escape, we said, was 100,000 years. All right, I think. Am I done with the first page? Eh? Done with the first page, that's it. Oh, here we go, last one. The last thing, the sunspot cycle is 11 years. And the magnetic cycle is 22 years. I'm not Mac. I am so not Mac. Okay. Sorry about that. Okay. All right. Chapter 10 is done. Chapter 11, are you ready? Jumping right forward. Okay. So the magnitude scale, chapter 11. The key thing about the magnitude scale, it was invented by a Greek guy, Hipparchus, and it's backwards. It doesn't make sense, but it makes sense. It's just not fun. It's higher numbers mean dimmer and lower numbers mean brighter. Okay, so we talked a little bit about, reasonable numbers. The numbers 1 to 6 were the original numbers defined by Hipparchus. We kept the 6, by the way. You're supposed to know that the 6 magnitude stars are the dimmest stars you can see with the naked eye. 7 cannot be seen. You can't see it. You need a telescope. Sorry, you need a telescope or some help. Okay, so there's the apparent magnitude as seen from Earth. And then there's the absolute magnitude, which means you move the star to a distance of 10 parsecs, 32.6 light years or 33 light years, something like that. And the idea is that absolute magnitude is not affected by distance anymore, right? Absolute magnitude is only the luminosity. So luminosity of something and the absolute magnitude of something are directly connected. Interestingly enough, the apparent magnitude of our sun, if you've written it down before, is negative 27, but the absolute magnitude is positive 5, right? If you take the sun and move it to 10 parsecs, it looks like a pretty dim star. It's not a super bright star. The key thing is that we know that mathematically there's a relationship, and if you know the absolute magnitude and the apparent magnitude, you can calculate the distance, okay? That's the one most important idea that you have to learn, right? So if you find a way to get the absolute magnitude compared to the apparent magnitude, you got the distance, okay? A Cepheid variable is a star that changes brightness, it changes brightness, it's periodic. So it pulses bright, dim, bright, dim, and there's a length of time for it to pulsate. And it was first determined, I guess we got to put her name, Henrietta Swan Leavitt, found the relationship, and I guess I can bring that up. Let's bring that up. Don't save. I don't know what I did. Bring that up. Chapter 11. Henrietta Swan Leavitt. Oh, you definitely need to know this relationship. Definitely need to know this relationship, okay? You need to know this relationship, not like specific numbers or anything, just the way it works, right? So the longer the period, the greater the luminosity of that variable star will be. That's the key thing, okay? The longer the period, the greater the luminosity, okay? Yeah, you kind of want to know that already. If I don't mention it, you're supposed to know that, okay? So Henrietta Leavitt was the one who invented that, and it became a really important tool for measuring the distance to things like galaxies that we couldn't do until we understood that principle. Okay. All right, man, I got to learn how to do this. Okay, so binary stars. What's a binary star? A pair of stars that orbit each other. One of the key things I think about is like center of mass, which we've talked about before. Does anybody want me to go over center of mass ideas? Everybody feel pretty good? Center of mass? Okay, good. So what happens is one mass is smaller than the other. The key thing is the larger mass will have a small orbit, small mass has a big orbit, and that means the speeds will be different, right, according to the masses. The one that's large will have a small speed, the small one will have a high speed, okay? So there are three ways to tell that stars are binaries. One of them is really difficult. The visual binaries, very difficult. Okay, you have to measure the position of the stars over time and see that they actually are changing and orbiting each other. So there's just a few stars that we know about. Although recent technology has improved, and this may become more important. So there's a kind of interference technique that's being done now that's actually making it more effective. But still, it's really small, not very effective. Okay, the next most effective is called. Well, actually, let me not say that. Let me tell you that the most effective method right now is the spectroscopic binaries. That is the most effective method. So we can't see the individual stars, but we see their absorption spectra. And because of that, we can see that one star is moving towards us while simultaneously the other one's moving away from us. So what we'll see is a blue shift and a red shift. The size of the blue shift and red shift tell us the relative masses of the stars. Okay? If they were the same mass, then you would get the same amount of red shift as you got blue shift as you get red shift. Okay, but we usually get different numbers, right? Different amounts. Now, the eclipsing binaries is a new technique. And now that we know how to find exoplanets so well, it may become as important as the other technique. It's still pretty new. So you watch the light curve of a star or a pair of stars, and you can see it getting brighter and dimmer. I'm going to come back to that and show you. I do want you to know a special situation, the red giant white dwarf situation. What does it look like when you look at that light curve when they eclipse each other? And that's kind of an interesting one. So I think it will become more important. But right now, spectroscopic binaries is the best method for detecting binaries. And it's been used for the last 50 years very successfully. Okay, we have two kinds of velocity. One of them we can see, and the other one is really difficult to see. Okay, so radial velocity is the one that we see with the Doppler effect, red shift, blue shift. That's radial velocity, towards us or away from us, right? But the proper motion is to the side, right? It's sideways. And that one, there's no Doppler effect. It's really difficult to see. You got to take a picture and then 5 years or 10 years or 50 years later, take another picture and see if it's moved. And that motion is really difficult to see as a result, right? So we can't automatically see that. Spectral classification, what are we talking about? So we're talking about Annie Cannon and the Harvard computers. Annie Cannon, you're supposed to know her name. She was the lead of the Harvard computers who were computing the spectra of stars. And they were organizing the data so that stars would have categories, categorizing stars, spectral classification. So we want to go ahead and bring up that slide for you. Bring up that slide. There's Annie Cannon. And here's the slide. Oh, be a fine girl or guy or something, kiss me, right? So O, B, A, F, G, K, M are the letters, and those are the correct order. What's happening, what was the reason for it? They didn't know until they'd done about 5,000 stars, is this is the order of the color of stars, which is also the surface temperature of the stars. The O stars are the hottest, and the M stars are the coolest, right? So they're in correct order in terms of the surface temperature. So if I ask you which one's hotter, you just look at that letter and you can figure it out, right? Which one's hotter, an F or a K? F comes first, that's hotter, right? Which one's hotter, a B or an A? B is hotter, right? Which one's hotter, a G or a K? G, okay. Oh, actually, by the way, speaking of G, what is the classification of our sun? G, right? A G2 and then Roman numeral V, right? Roman numeral 5, G2V. Okay, you're supposed to know that. I actually have that on the study guide too. All right, proper motion, component, Hertzsprung-Russell. Okay, Hertzsprung-Russell. What's a Hertzsprung-Russell diagram? A diagram which shows a bunch of stars in one picture. And here is an example of a Hertzsprung-Russell diagram. It shows a bunch of stars in one picture. If the stars are, so we've defined different kinds of stars. We've got stars that are on this branch right here. This is most of the stars, 90% of the stars, which is why we call it the main sequence. 90% of the stars are on the main sequence. Why? Pretty simple reason. What fraction of their life do they spend on the main sequence? 90% of their life. So 90% of them are on the main sequence, right? 10% of them are not, right? So what about the other ones? So we've got the main sequence. What is this bunch of stars down here called? They're kind of small, but pretty hot. They're called white dwarfs, right? This is the white dwarfs. And then we have above the red dwarfs, which are on the main sequence. We go higher, we've got the red giants, and above the red giants, the red supergiants, right? So you know those names and you know where they are, okay? Now on the main sequence, we're going to talk about all the trends, but this is the basic idea. Look at the temperature scale. Where's the letter O? Starting over here, right? This is O. And be a fine girl, kiss me, M down here, right? M is the coolest star. Are there a lot more O stars or M stars in the universe? Lots more M, right? Lots more M. I don't know, should I write down the statistic? 1,500 M-class stars to every other kind of star combined, right? 1,500 to 1, right? So lots and lots of M-class stars. When you guys, at the end, if you want to sign in to get credit, and there's snacks over here if you want snacks. Help yourself. Okay, so the main sequence, giant, supergiants, red dwarf. Okay, so the one thing that's not labeled is the red dwarf. What does red dwarf mean? One more time. A red star, an M-class star on the main sequence. So it's pretty small, and it has the same temperature as a red giant or a red supergiant, but it's really, really tiny. Okay, so the reason for the difference in the giant, supergiants, and red dwarf, they're all the same color. If they're the same color, they have the same surface temperature. But what's different? Why is there a giant, supergiant, dwarf? What's different? The luminosity is different, right? They have different luminosities. So how do you get a higher, with the same temperature, how do you get a small luminosity? You're a small size star, right? The larger you are, the more luminosity you have. So the giants are pretty big. They're huge. But supergiants are even bigger than that, right? Because they're putting out more light. Each square meter puts out light. The temperature determines how much light comes out per square meter. But if you're in the same temperature, vertical line, you have to be larger to put out more light. That's the only way. Okay, life expectancy on the main sequence. Okay, we're going to talk more about that. But as you go up the main sequence, take a look right there. As you go up the main sequence from the lower part to the upper part, what's changing? Okay, the reason stars are sitting on their position on the main sequence, what's the key factor? The mass. It's all about the mass, right? So if you find 6001 right here, this is our sun right here, G-class star, G2V. But if you go down the main sequence, what happens to the mass? You get bigger or smaller? Down the main sequence, you get smaller. What's the smallest mass star? I'm going to bring it up in a few minutes anyways, but you got to memorize the number. What's the smallest mass star you can have on the main sequence? 0.08 solar masses, 8% of a solar mass. That's the smallest star that will light itself up and keep lighting up and actually live for how long on the main sequence? 5.5 trillion years. kind of crazy. We've never seen one die because the universe has only been around 13.3 billion years, right? How about our sun? What's the lifetime on the main sequence? One solar mass, 10 billion years. And the last one, if we go way up, actually even past where I see stars on this picture, 100 solar masses at the very high end, very hot O-class star, would only live how long? 100,000 years, 100,000 years, which is kind of crazy small for stars, right? So that's the main sequence lifetime. Okay, what's a turnoff point? Supposed to know turnoff point. There's two kinds of clusters in this world, open clusters and globular clusters. One of them is made of new stars. Which one's new stars? Open clusters, and they are going to drift apart eventually and not be in a cluster eventually, right? So our sun was born in an open cluster, and we can't see the rest of those stars anymore. But globular clusters are so many stars that their gravity keeps them together. So they're interesting. Which ones are going to be old? The globular cluster is made up of old stars. So if you look at an HR diagram, you're supposed to be able to immediately tell, is that a young cluster or an old cluster? So I'm just going to do the examples. And you see if you can figure it out, right? What are the different pictures that you see? So the pictures are the HR diagram. So we have not the complete main sequence, but we have missing stars. Okay, I got two HR diagrams. So here we have O, B, A, fine girl, kiss me. And we have the luminosity with the luminosity of the sun as our scale. And then we have something like this, the main sequence. Okay, so actually I should have done that in dotted. Let me do a dotted line. So here we go. There's a dotted line, and I'll do it again. Luminosity going up. There's a 1. O, B, A, fine girl, kiss me. Okay, oh, I did it again. Sorry. Oops, I did it again. Okay. Any Britney fans in the house? All right. Sorry, mumbling. Okay, so this is we're supposed to be the same picture. They're not quite. And I'm going to just randomly decide to do one thing or another. I'm randomly deciding. Okay, I'm randomly deciding to do this. Okay, this is the turn-off point here. And I'm randomly deciding to do this. Okay, so look at these pictures and tell me which one is a young cluster and which one is an old cluster. I've tried to make it simple. Which one is which one's old, which one's not? Which one's old? Old cluster. The right or the left? Old cluster. The right. Why is this the old cluster? Old cluster. Old cluster, globular. Which ones are missing? Which ones have left the main sequence? The large stars have left the main sequence already, and the young stars are still there. The small mass stars are there. Remember that larger mass lives and dies quickly, right? So they leave the main sequence very quickly. And so if you find the turnoff point, that's the turnoff point. In both pictures, there's a turnoff point. You can say what the life of the cluster is from that, right? So the star that's just missing, you can go look up. What's its main sequence life? That's how old the cluster must be. On this one, what's missing? The small mass stars have not gotten there yet, right? They're on their way. They haven't gotten there yet. And so these stars are going to end up, doing their thing to get down to the main sequence, but they have not gotten there yet. So this is an example of what kind of a cluster? An open cluster, which is young. Okay, got it? Okay, so I would suspect that you have one or both pictures on your exam and you can quickly say which is which because of that. So what does the turnoff point give you in either case? The age of the cluster, the age of it, right? So this one, you know how long it takes a star with this mass to get to the main sequence. And so you could say that's how old the cluster is as well, because those stars are not there yet. All right. Okay, globular clusters we just mentioned are young or old? Which one? They're old. They're as old or older even than the Milky Way. And we have 150 orbiting the Milky Way right now. What about metallicity? What's metallicity? Metallicity is the term for enrichment, right? How enriched are the stars? The main ingredients of stars, hydrogen, helium, but enriched with other things, right? And every generation of stars enriches the next generation. So the higher the metallicity, the younger the star must be, right? So a very old star, the first generation star, has almost no metallicity, but each generation becomes enriched by the explosions, the supernova that come before it, that started the next generation. Everybody good? Okay, you guys are gonna stop me if you have questions, if something I'm saying isn't clear, right? Okay, because basically you're just sitting there, but that's cool. We're good, we're good. You can ask questions too, You got that, all right. How does the brightness change with distance? How does the brightness change with distance? This is not a quantitative class. I shouldn't forget to plug my quantitative class, but if you want to calculate distances, I do that in the astrophysics. We do that all the time. That's just for fun. It's like for fun. But anyways, what happens? The further away you get from the star, what happens to brightness? The dimmer it becomes. But the question I'm asking is, how does distance affect brightness? What if you double the distance? What happens to the brightness? It's 1/4 as big, right? If you go 5 times as far, 1/25. 10 times as far, 1/100th, right? The distance squared is in the denominator. So the further away you go, the dimmer the light becomes. How is parallax measured? Oh, what the heck, parallax? Where'd you come from, parallax? Okay, parallax is a mechanism for measuring distances. Actually, I realize I don't have all the different distance measurements. Oh, well. You're supposed to know those. Maybe it's coming. Must be in the next chapter. Yeah, it must be coming in. I don't know. Is it in this chapter? Does it say the ladder? Where's the ladder? I think we just did distance right here. Okay. I mean, I don't have the ladder. Huh? Where's the distance ladder? Oh, you know why? You don't learn it yet. It's coming up. Sorry. Okay. Shh. Okay. Getting confused. We learned that after the test. Okay. Sorry. Okay, that's why. There's something really cool, right? So we're going to learn more techniques for finding distance. Okay, yeah, we're just beginning. I forgot. Okay. All right, so in the beginning, the closest stars we measure parallax, and you need to, and do you guys remember the drawing? How does it work? How do you do parallax? Anybody want me to review, or one person raise your hand if you want? Okay, so the review is, how do we make measurements from Earth? We take pictures, okay? So parallax pictures require us to observe a star, a nearby star. Ooh, I could turn it around. I don't know, which more work? I don't know, I'll just erase it. You guys like this board? Yeah? Is it clearer than the chalkboard? Yeah? Okay. I'll keep doing it. Okay, so there's a star over here that we're trying to measure the distance to. And we're on Earth, but we're actually orbiting the sun on this orbit. And so the idea is we take pictures at different times. One picture is here. We take a picture of that star, and we can see that it's in this cluster, or next to these stars over here from this perspective. And then we take another picture. When do we take the next picture? When we're on the other side of the Earth, the orbit, right? So how much later? 6 months between pictures, right? So you want to take a picture from as far away as you can get. And the idea is there's a new cluster that we're going to be in as we look from that, okay? So when we measure this, this is called parallax. This shift in position is called parallax, and the parallax angle is defined to be just half of it. But in fact, we do measure the total change. And then the key thing you're supposed to know about this is the distance between measurements is called the baseline. Okay, the baseline. So the larger the baseline, the more precise the values of parallax are. So we actually want it to be bigger, but we're stuck on Earth, so we can't make it any bigger than that. What is the baseline of observations from Earth? So it's 1 AU from the sun to the Earth, which means the distance from observations is 2 AU. 2 AU. That's the best we can do right now from Earth. If we launch a satellite and orbit Mars and do the same thing, we'll now have about a 3 AU a baseline, which will get us better results. There's a little problem. It takes longer to go around the orbit. So you have to wait longer. So this is 6 months between orbit pictures, but on Mars, it'll be closer to a full year. Actually, close to a year, actually. Yeah, that's true. Okay. Did I cover that? Parallax? So what's it good for? How far can you measure parallax? You don't really need to know this number yet, but might as well write it down. It's good for 1,000 parsecs. 1,000 parsecs, which is not very big. That's 3,000 light years, but the Milky Way is 100,000 light years across. Okay, so it's really not a great method for finding the distance except for the closest stars. So it's a way that we can measure the distance to the closest stars to Earth. It's the first step that we make in order to do that. Okay, so what happens, what's a standard candle? So I mentioned the idea already, but standard candle means that you know the blank and you measure the blank and you compare the two to find the blank. Okay, so you start with this one. You know the absolute magnitude. You measure the apparent magnitude in order to determine the distance, right? That's the standard candle method. So it turns out we just learned new techniques, better and better techniques for finding that distance, but it's the same principle every time. You know the absolute magnitude and compare it with the apparent magnitude, find the distance, okay? Okay, so I'm actually gonna give you some examples. Let's look at some examples. This is actually, usually people have trouble with these. Oh, I put these on your preview questions, didn't I? That's right. Okay. Yeah. The reason why, more than half the class messes it up. More than half the class. Not you guys. You're the other half. It doesn't mess it up. But anyways, maybe one or two of you, maybe. But let's take a look right here. So apparent magnitude is measured from where? From Earth. That's Earth right there. And absolute magnitude is measured from as if it was at a distance of 10 parsecs, right? So we've mathematically moved it to that position of 10 parsecs. And so when you look at these two numbers, are they the same or not? Actually, let me ask you a quick question. This is kind of a, think about it. Is there a way that these two numbers would ever be the same? Is it even possible? Give me the situation. In what scenario would those two numbers be the same? When the star is already at 10 parsecs, right? And then you don't move it, so the number doesn't change. Yeah, that's right. Thank you. Okay, so that's kind of irrelevant, isn't it? But actually, if you get that idea, if it was already at 10 parsecs, it wouldn't move, and therefore these two numbers would be the same. But what we're doing is mathematically moving it, right? So can you tell me, is this number and this number, which one is brighter in the magnitude scale? The negative number is much brighter than a positive number, right? So when you moved it, when you go to this column, what happened? It got brighter or dimmer? It got dimmer. Where did the star begin? Closer or further than 10 parsecs? So we moved it further away and it became dimmer. It started 2.6 parsecs. Does that make sense? So just ignore this column. See if you can figure it out without that, right? So how about this? 0.4, 2.68. Did it get brighter or dimmer? It got dimmer. That number is higher, which means a dimmer star. And sure enough, it must have started closer than 10 parsecs. But they're not all like that. Let's find one where the number gets, how about this one? Achernar, or Capella. How about that? I like Capella. Easier. Capella, 0.08, negative 0.48. Got brighter, right? What does it mean? Capella must be further away than 10 parsecs. When you move it to 10 parsecs, and sure enough, it's a 12.5. Okay, so is that simple? Basic idea. Okay, so what happens when you move the star to 10 parsecs? Does it get brighter or dimmer? That was a trick question. What's the answer? It usually changes, right? It gets brighter if you move it closer, and it gets dimmer if you move it further, and it doesn't change if you're one of the few stars that are actually 10 parsecs away. All right, describe common center of gravity. Can I skip that part? We already talked about it. I mean, I'll do it again if anybody at home want to see that? Okay, we hear you is the last comment I heard. Okay, so apparently not. We good? Okay. Differentiate between proper motion and radial velocity. Again, I think I talked about that. Radial velocity means what? Going towards you or away from you along a radius. That's what's called radial velocity. Proper motion is across your field of view, and you can't measure that very easily. This one, you use the Doppler effect. This one's really difficult to do. Okay, now, I put it in here, so I think right now I should show you a picture that's probably on your test, so you can handle it. But it's not in our slides. I don't know why. I just never put it in there. I should have. I would like to. I should add that. Eclipsing binary light curve. Oh, that's cute. That's actually real. I don't want to deal with that, even though it looks really cool. Oh, that's pretty cool too. Yeah, let's do that. Let's do that. Look, there's no, you want to see the pictures? We better see this is still a review. Let's look at pictures. Never mind. Okay, I want to do the one without any pictures, but I think maybe we could go back and figure it out, right? We'll figure it out. So the idea is that there's two dips in the light curve for this one. An eclipsing binary is one where one of the stars is being eclipsed by the other one. Okay, so this is a particular kind of combination that you're supposed to be aware of. Red giant, white dwarf. Which one's hotter, the red giant or the white dwarf? The white dwarf is much hotter than the red giant. So what happens to the size of the dip when you eclipse the white dwarf? You get a big dip because you're losing all of the light from that little hot star. But when you eclipse the red giant, you get a little dip because you're only blocking the amount of light that would come out of that size, which is much, much less than what came out of the white dwarf. And so you get a small dip, right? So these ones are very interesting because they show that, right? Big dip, little dip. When do you get the big dip? When you're eclipsing the hotter star, right? The hotter star is being eclipsed, you get a bigger dip. So if I show you this one right here, it's the same data. I mean, this is real data, which is kind of cool, right? That's real data. Which one is which? Where's the white dwarf behind the red giant? In this one or this one, right? Where's the red giant behind the white dwarf? This little dip here, okay? You guys got it? Okay. All right. Light curve. Identify the major categories of the HR diagram. I think I've already done that too, right? Main sequence, 90% of the stars. White dwarfs, little pocket down below, hot, small stars. And then we have above the M, we've got the red giants and the red supergiants. Question? Oh, sorry. You're just thinking about it, visualizing it. Okay. I mean, we could bring up an HR diagram too. HR diagram. I should mention something. Some HR diagrams have, instead of luminosity, they have absolute, like this one right here, has absolute magnitude. So that's a little confusing, but it's the same idea, and they're related to each other. Absolute magnitude is connected to luminosity. So whether it's absolute magnitude or luminosity, it's the same diagram, okay? The numbers change as a result, that's it, okay? You get the main sequence, the white dwarfs, and the giants and the supergiants. And subgiants, we don't do that. Don't worry about that. Any questions? Got that? All right. All right. Okay. Okay, how is the lifetime on the main sequence determined by your position? Because what determines your position on the main sequence? Why are you at some spot? What determines it? The Mass, right? The mass. So the mass is also your lifetime. So if you're a 1 solar mass star, like our sun, how long do you live on the main sequence? 10 billion years. If you go higher, you live less time. You give lower, you live longer time. Are there stars on the main sequence that have longer than 13.3 billion years? Yes, and those ones will have never died, right? A star with that kind of a mass will have never died because the universe is only 13.3 billion years old. So there are stars that are still alive and could have been born at the very beginning of the universe, right? They're still alive. We don't know where they are, but they must exist. We know some of them. Okay, and I'm just giving you a hypothetical. We've actually never seen large mass first generation stars. We've never seen that. We've seen lots and lots of red dwarfs that are old. Anyway, so turnoff point, we talked about that as well. I think I skipped that. Okay, range of human seeing. Okay, I guess I need to talk a little bit more about magnitude. The magnitude scale changes a number if you get brighter or dimmer. But if you change by one number, how much does the star change its brightness? Remember the number? 2.5, right? So each step that you take is a factor of 2.5. So one magnitude number difference, the one that's lower is 2.5 times brighter. Okay, so blah, blah, blah. Okay, I didn't put that up there. All right, no example. But like any two numbers. Give me a number. Give me any number. Somebody give me a number. What was that? 5. Okay, 5. So what's one number brighter than a 5? A 4. Okay, what's one number dimmer than a 5? 6, right? So the difference in brightness between a 4 and a 5 is 2.5 times. A 4 is 2.5 times as bright as a 5. But a 5 is 2.5 times as bright as a 6. One step is 2.5. If you take 2 steps, the difference is 2.5 times 2.5, 6.25 times. And if you take 5 steps, then the difference is 100. So I gave the example of a 2 and a 7. That's 5 steps. And 2 is the brighter one. It's 100 times brighter. That's actually from Hipparchus, right? Anybody remember this stuff, right? The degree is way too big. Parallax are measured in seconds, arc seconds, and there are 3,600 arc seconds in 1 degree. So it's really tiny. That's why it's so hard to do parallax measurements, and why Aristotle was convinced that we weren't moving, because he couldn't see it. But he didn't have the technology in that day to measure it. Okay, the closest star is. Did I ask you to know the name? I didn't put it on the study guide. Anybody know the name? Alpha Proxima Centauri, and it's 4.2 light years away. 4.2, 4.3, actually, what is it? 4.2 or 4.3? Forget. Anyways, it's closer, it's further than 1 parsec. And so the parallax angle is less than 1 arc second, as a matter of fact. Okay, oh, be a fine girl, kiss me. That's it. And then last thing, which we said already, but let's do it again. The lifetime of our sun on the main sequence, 10 billion years. The smallest mass star that can light up, 5.5 trillion years. 100 solar mass, 100,000 years. Okay? Oh my gosh, I have to get 3 more chapters done. I got to go faster. Holy mackerel. I think I should have gone faster. Oh well, I'm going to speed up now. This is a boring chapter. This is super quick. Chapter 12, wrong computer. Okay, chapter 12, interstellar medium, okay? Interstellar medium means what? The stuff between the stars. The main things, I even dropped the 2 that I think are kind of boring. I have molecular clouds, the coolest. H1 clouds, a little warmer, and H2 clouds, quite a bit warmer. Photoionization, a bunch of words. Okay, let's talk about these clouds real quick, or these ISM. So molecular clouds are incredibly cold, right? They have molecules in them because they're so cold, like 10 K, and they're incredibly dense. Are they good star-forming regions? Absolutely, they're great. In fact, all 3 of these are if there's a high enough density, okay? How do we see molecular clouds? Can we see them? Are they emitting light? Not really, because they're so cold, we can't really see that light. What we see is the light that comes through them, we see absorption lines coming when we look at that light. So the absorption spectra is the best way, okay? H1 clouds are made primarily of neutral hydrogen. Neutral hydrogen does not glow. It's cold, like 100 Kelvin. Does not glow with a temperature, with a high enough glow. We don't see it. But we do notice, again, absorption, and we especially notice a certain frequency, a certain wavelength of radio wave called the 21 centimeter wave you're supposed to recognize. So the way that we saw the neutral hydrogen in the very early days was radio astronomers noticed this 21 centimeter radiation coming in very distinctive bands, and that was the first way to see it. H2 is photoionized hydrogen, right? So it is not neutral anymore, it's ionized. And well, it could be photoionized. This is ionized. Sorry, it doesn't necessarily mean photoionized. It's H2 clouds are hotter hydrogen, like the surface of the sun. So they glow with a very distinctive color. What color is a distinctive glow when we see an H2 cloud? The red color. We look for red. Okay. Photoionization, I have to be a little careful. Sometimes it's from photoionization, sometimes from other heat sources. Okay. But photoionization says that a hot star behind a cloud can make it start to glow. And so often this is happening. There's a hot star behind it, and the light of that star, ultraviolet light or other high energy photons, are causing the electrons to be ripped off. And then when they fall back on, they emit light. Okay, it's called photoionization. Light ionizes the electrons. Reflection nebula, not a big deal, but it doesn't glow with its own light. So these are going to be emission nebulas, H2 clouds. The reflection nebula, the light of the star is reflecting off of the dust, and you see the color of the stars, not the color of the dust. A Bach globule is a special kind of beginning of a solar system. We see it's dark. It's a dark region. And we think it's some matter that's falling together but hasn't formed a protostar yet. So it's before the protostar stage, but we think it's part of the life of a solar system. So we look there in a couple 100,000 or 1,000,000 years, we're going to see a protostar. Free fall time refers to the time when a gas cloud is collapsing, and the higher the mass, the shorter the free fall time will be. The lower the mass, the longer the free fall time will be. Those are the ideas that you need to know. Okay, Herbig-Haro are about half of the young solar systems, protoplanetary disks, have jets shooting out of them. The jets are magnetic, right? We know that they're magnetic. We don't know exactly how they work, but they're definitely North Pole, South Pole magnetic jets. And they're called Herbig-Haro objects. CNO cycle, blah, blah, blah. I don't think you care about that. We already talked about it. And open star cluster, we've talked about that too. But a brown dwarf is a term that we haven't talked about today. So I just want to mention what that is. Brown dwarf is a star that does not have enough mass to sustain nuclear fusion. So it is less than 0.08 solar masses. It will never ignite, okay? Never ignite. Okay, so describe differences in the interstellar medium, be able to describe the type of light and the source of their energy. Compare the light from an emission nebula with a reflection nebula. Okay, so I guess one more time. So what about the molecular clouds? Oh, so what clouds did I leave out? I left out the WISMs and the coronal gas. It's unlikely that they're on this test at all. They're going to come up again, though, coronal gas especially. So it's not that I don't care about them. I just didn't put it on the study guide. Yeah. One more time.
You mentioned reddening.
Oh, interstellar reddening. Yeah, I know. I don't put. It's not on the study guide. Not on the study. Did I have it on the study guide anywhere? No, it's not on there. There's too many things. There's too many things. Yeah, I put it in class, but you could forget it now if you want. I mean, you don't have to forget it. It's just there's too many things. I didn't put it on the study guide. It's a tiny detail. It's cool, but yeah, we don't need to worry about it. Okay, so one more time. So molecular clouds, how do you see them? With molecular absorption spectra. How do you see the Neutral, hydrogen 1, H1 regions from 21 centimeter radiation. And how do you see the H2? From the visible light. They have emission. They emit light because they're like the surface temperature of the sun. They emit a lot of light. Okay, so emission and reflection nebula, relationship between free fall time and the mass. I already told you what that was. What's the relationship? Higher mass, shorter time. That's it. Describe the likely reason for the jets. I just told you that a second ago. What were they? Magnetic field. So there's a region. Okay, I'm going to throw this word in because we need it in a few minutes anyways. The material that's orbiting the protostar is a disk shape, and this disk is called the accretion disk. That's what's that hot, charged up disk is making the magnetic field. It's the circulation of charged particles that creates the dynamo effect that makes a magnetic field. We see it in many other places too. And I did this already, and I did that already. Okay, I'm ready to jump to chapter 13. Are you guys ready? Anybody? Did I miss anything? You're watching me, okay? If I don't cover something, tell me. Okay. Ay, ay, ay. How am I going to do this by 4? Some of this stuff you don't even know yet. Oh, okay. We just do our best, okay? All right, here we go. Type 2 supernova. What's a type 2 supernova? A massive star greater than 8 solar masses that keeps burning fuels, heavier and heavier elements until it gets all the way to the end. What's the last element? Iron. Gets all the way to iron. Goes all the way to iron. So more than 8 solar masses will go all the way to iron. Just anybody more than 8, you're going to go all the way to iron. And when you do iron on that day, what will happen? Your core will collapse, and then the other layers, which are also burning, are going to collapse behind it, and then rebound, collide, explosion, and it's a supernova. It's an incredibly powerful event. In a single moment, we have more light coming out than the lifetime of our entire sun, right? The whole lifetime of our sun, a whole 11 billion years. It's more light than that. I mean, it's just unbelievably bright, really, really bright. Okay, so yeah, hydrogen shell burning is the next stage of our sun's life. When does the hydrogen shell burning begin for the sun? So maybe we'll walk through that real quick. What's the stage of our sun? What has happened to make hydrogen shell burning start to occur? Yeah. So what happened in the core? What happened in the core right before this? What was it? Well, we ran out of our fuel, which has been hydrogen. So we ran out of fuel in the core. So the core is not fusing anymore. So what happens to the core, you say? It begins to contract. And as it collapses, it's not collapsing completely, it's just heating up. And as it collapses, it heats, and then the outer layer now reaches the temperature needed to fuse hydrogen. And so you get hydrogen shell burning. What stage of the sun's life will this be called? After main sequence comes red giant stage, right? This is the first of the 3 red giant stages, okay? So the second one is as the core is not fusing, it will continue to collapse because there's not enough radiation pressure to hold it up. And what's happening as it collapses? It's heating up. Eventually it reaches, I think I make you learn this number. Do you memorize this number? I don't remember anymore. No, I didn't. Okay. Never mind, I didn't make you memorize it. But the temperature of fusion for helium is 100 million Kelvin. And so it takes a while for the core to heat up to that temperature. So the key thing is, as it collapses, it gets hotter and hotter and hotter. One day, it's hot enough to fuse helium, and the helium flash is that moment it ignites. So now you've got simultaneously burning helium in the core, hydrogen in the shell. Both of those are happening. What happens to the size of the sun? It gets even larger, right? So the sun has 3 distinctive red giant phases. We're just going to call it red giant, but really be aware there's 3 different time periods, right, that you want to think about. And the helium only lasts for maybe 100 million years, not that long. And then it's gone, right? And what will happen to the core at that time, at that point? It's made ash out of, what does helium make? Makes carbon and oxygen. So the ash of carbon and oxygen will collapse. And will it eventually ignite? Not in our sun. In larger stars, yes, but not in our sun. And so we'll never fuse the carbon. We will just eventually collapse that carbon. But as it does, it gets hotter and hotter, blah, blah, blah. Oh, yeah. And then what happens to our sun? So we ran out of helium. We're still burning hydrogen in a shell, but the core is collapsing. And then suddenly it gets hot enough outside the core to fuse helium. And so you get helium shell burning and hydrogen shell burning at the same time. More energy, big star, right? So the sun will pulse with energy at different times in its life. And as a result of this, something really beautiful happens. The sun will lose 80% of its mass as every little burst of energy sends off a wave of material. It's not held very strongly, so any extra force just pushes it away. And so you have shells of material that are going away from the sun. Now, also, in the process of growing, it eats planets, right? And we know that the planets stir up the insides. And then so there's another factor. Maybe it's the stirring of the planets or maybe a companion star. But something interesting happens. The clouds that are escaping from the star can be kind of interesting, not just spherical, but have lobes that go in different directions. And those are called the planetary nebula. Okay, planetary nebula. The mass that's escaping from the original red giant, right? Red giant we're talking about, that will eventually light up. When do they light up? When does a planetary nebula light up? When the star has run out of energy in the core, no more helium. No more helium, right? So no more helium. We got carbon and oxygen. We run out of all the other energy. We've blown away most of our mass. The core has nothing left. It just collapses down and forms a little ember called a white dwarf. The white dwarf is so hot that it shines primarily in what color of the spectrum? What kind of light comes out? So hot, 100,000 Kelvin. In ultraviolet, right? So this ultraviolet light shoots away from the white dwarf, hits the clouds of gases that have been leaving, and they glow for about 500 years. And so the planetary nebula is a temporary glow that we can see for about 500 years, which is the remnants of a red giant or a red giant. Let's say red giant, okay? Roche lobe, okay. Yeah, because I got to talk. Yeah, I definitely got to talk about that. Okay, the Roche lobe is a concept that in a red giant white dwarf system, that if the matter gets far enough away from the red giant, it can be captured by the white dwarf. So the Roche lobe is when matter gets close enough to the white dwarf to grab it. Okay, what happens to the white dwarf in that binary system when it grabs matter from the red giant? You get something happening. It lands on the surface and flash. It makes a little brilliant flash called a nova. It's called a nova, right? Novas can happen time after time after time. And every time a nova occurs, a little bit of mass is added to the mass of the white dwarf. Okay? So what is the Chandrasekhar limit? The Chandrasekhar limit was first determined by Subramaniam Chandrasekhar, who studied the electron degeneracy pressure. Okay. Before I get to that, let's talk about the white dwarfs. What are white dwarfs? What are they? What are they made of? What are they? Right? Are they made of atoms? What kind of atoms are white dwarfs made of? Carbon and oxygen. Okay? And so they're compressed down, and gravity's compressing it together. But what stops gravity from compressing it any further? And the answer is the electrons, right? And the way that we talk about that precisely is the name that we give the force that the electrons have is called the electron degeneracy pressure. If you want to study more about this, in fact, I can tell you the key thing, the word degeneracy means the electrons have the same energy. They're in the same energy state. And they're not connected to one atom anymore. They're on the white dwarf. And there's like a sea of these electrons. But they don't want to get smushed together because they're all negative, right? And that pressure is what's holding up the white dwarf and keeping it from collapsing. You don't need to know all that. What you need to know is the word electron degeneracy pressure is what stops gravity in a white dwarf. Which one's stronger? Trick question. What's the answer? They're balanced, right? They're balanced, right? So the electron degeneracy is strong enough to stop gravity. However, the Chandrasekhar limit says that there is a maximum mass white dwarf that the electrons can't hold back gravity anymore. And that number you need to memorize is 1.4 solar masses, right? That's the largest mass white dwarf that you can have. So any more mass, the gravity will be too strong, and the electron degeneracy pressure will not be adequate to hold it back. All right, talk. Okay, now, if you did have more than 1.4 solar masses, then the electrons would not stop gravity, and what would happen to the electrons? The electrons don't stay outside the nucleus anymore. What happens? They get pushed into the nucleus, and so you want to remember that if you have more than 1.4 solar masses, then the electrons get pushed in with the nuclei, they find protons, and what do they become? They become neutrons, right? So you get something very strange called, so if the electrons are forced into the nuclei, they find protons and they form a big ball of neutrons, okay? This is incredibly dense, right? This is only about 10 miles across, which is like 16 kilometers. Okay, and it has more than the mass of our sun. It actually has a mass as a neutron star. So between 1.4 and about 2.4 solar masses. Okay. Okay, so now what is it that stops the neutron star from collapsing? And this time, it's not electrons, it's the neutrons themselves. So this is actually, there's no empty space here. These are neutrons pushing on each other. It's incredibly dense. There's almost nothing more dense than this in the universe, right? Nothing that we can see, nothing that we can interact with. Okay. Yeah. Where am I going? Neutron degeneracy. Okay. Neutron degeneracy pressure is the name of the force. Okay. What happens if you have more than 2.4 solar masses? What can stop gravity? Nothing can stop gravity. Okay. So I did that table in class. Does anybody not get that table? Where what happens to the star? Should I draw it again? Review it? Okay. Here's a quick table. You want to memorize the thing right here. Okay, so what were the fields? We had the starting mass. Okay, let me see if I can get this in here. The final mass, the final, actually, let me put remnant mass. Okay, and then how they died. How did they die? And the object. And the force against gravity. Okay, so if your starting mass is from up to, so it's less than 8 solar masses, you're going to end up with less than 1.4 solar masses when you're done. So what are you going to be? You're going to be a white dwarf. Oh, how did you die? You just collapsed. You collapsed when you ran out of fuel. It's kind of a whimper. It's quiet. Nothing, no big deal, right? What do you get? It's called the white dwarf. And what's the name of the force? Electron degeneracy pressure. Okay. Electrons. Okay. Now, what if you have between 8 and 20? Okay. Turns out your remnant mass is going to be between. Thank you. I'm too slow, huh? Okay. How did you die? It's called a type 2 supernova. What do you get? It's called a neutron star. And that's neutron degeneracy pressure. Okay, and then we go all the way right? If you have greater than 20 solar masses, you're going to have greater than 2 point. I put 2.4, didn't I? Okay, all right, let's go ahead and put it. You still died in a type 2 supernova. And what do you get? A black hole, which we will talk about in just a second. So what stops gravity? Nothing. Nothing can stop gravity. Gravity is too powerful. You cannot stop gravity. Okay? Okay, all right. So that's a review. I don't know how I could finish this in 20 minutes. All right. I'd have to go a little longer. You guys can always leave and then watch the review later. Okay, or I'll stay, whatever. Okay, here we go. So there's a word nova, real quickly. What is a nova? It's when a red giant white dwarf combination, red giant dumps matter onto the white dwarf. Okay? And what is a type 1a supernova? Well, what happens to the mass of the white dwarf every time a nova occurs? It's a little bit larger. And there is a day when the nova occurs and it goes over the limit. And on that day, it can't be a white dwarf anymore. The electron degeneracy pressure is not great enough. And so the thing just collapses, and almost instantaneously, all that carbon and oxygen fuses, releasing in a runaway thermonuclear reaction called a type 1a supernova. Okay? So type 1a is very distinctive. It's a white dwarf that goes above the Chandrasekhar limit. In order to do that, it has to have a companion to feed matter to it, right? It has to be a very special situation. So most white dwarfs do not do this, right? It's just got to be just the right situation. It's got to be large enough that somebody can keep feeding it and one day go over. And so it's got to be in a binary, and it has to be close enough that it can explode. But they do happen, and they happen in and they happen all over the place. And they also are something that always happen the same way. We know the mass of a type 1a supernova is 1.4 solar masses. Therefore, we know the absolute magnitude of it. So if we see one go off anywhere in the universe, anywhere, we can measure the magnitude, the apparent magnitude, and from that calculate the distance, right? So they're pretty amazing. They're one of the best standard candles. Okay, weak nuclear force is actually describes how the proton and the electron can combine and form a neutron, or how the neutron falls apart. That's actually all you really need to know. Although we will talk more about that in the next chapter after you take the test. There's a very interesting thing you need to know about. Stellar ejecta, stuff that gets spewed out during an explosion. What happens is a shock wave and material goes exploding out. What's going to happen with all that shock wave and material? The material goes into the interstellar medium, and the shock wave starts new seeds, which will become new stars. So the death of a star is the beginning of the lives of the next generation of stars, right? That's how it works. Thermonuclear runaway is what I mentioned, happens inside of a type 1a supernova. Supernova light curve, it brightens and then dims, and you need to know where that peak is in order to know the apparent magnitude. Okay, you want the peak apparent magnitude, and that way you can determine the distance. Okay, pulsar is a special kind of neutron star. It is a rapidly rotating neutron star. And I think I didn't cover this in class, so this is kind of a part that you want to be aware of. There's a term that we use, it's called the lighthouse model, and it says that there's jets of energy and particles that are shooting out of it because of its magnetic field. And if we get hit by it, we get a signal. We can see light. It was first detected in the 60s by a woman named Jocelyn Bell. And Jocelyn Bell had one of the first, as a graduate student, built a radio antenna array. Before there were big radio telescopes, she built a radio antenna. And she started using it with her advisor. By the way, her advisor got a Nobel Prize for it. She got almost nothing. It was really cheap. And then in 2006, people went back and go, she was kind of wronged. She did all the work. An advisor, Hewish, got all the credit. But now we look back and we understand it was mostly her work. So Jocelyn Bell. Oh, actually, I'll just show you the slides. Next chapter, sorry. Okay. Okay, here's Jocelyn. And this is the first signal that she got. This is called a pulsar. She got regular beeps, and she was actually really confused at first. She thought that maybe she was reading a secret military mission, something, because it was definitely man-made. Look at that signal, right? Nothing in nature makes signals like that, except that when she finally did parallax measurements, she realized it wasn't on Earth. It wasn't even close. And they didn't know what it was. So she and an advisor sat on it. We're like, well, that's our first one. We'll just wait. And they found 3 more. They still didn't know what they were. Each one had a different frequency, but they were these regular pulses, right, of energy, radio energy. Is why they're called pulsars, right? What's happening is the pulsar beam was sweeping across the Earth. So pulsar. Oh yeah, that's pretty cool. All right. I did this in class, right? So the idea is if the jet points towards the Earth, then we see it, right? And you don't just see radio waves, it turns out you see visible light as well. So when we finally learned how to look for them, we could see visible pulses coming from these things. And some of them are rotating so quickly, almost 1,000 times per second. They're called millisecond pulsars because their periods are on the millisecond range, right? They're just a few milliseconds each. Okay, so you don't see it all the time. You see pulses every time that beam hits the Earth, right? Okay, so what they didn't know what they were. So you guys have never heard this stuff before. I should probably just tell you a little story. And so they wrote an article and they said, we don't know what these are, but we're going to give them a name. LGMs, right? LGMs. Who knows what LGM stands for? Little green men, right? They actually thought maybe they were listening to aliens. They didn't know. And it was only later that we understood that this is a rapidly rotating object, a neutron star. And in fact, how do you know that something like this is going to rotate so quickly? What makes it rotate so quickly? What principle did we already learn about? Conservation of angular momentum. That principle tells us that if you squish it down really small, it's got to rotate incredibly fast to compensate. Okay, so neutron star, gravitational wave. Oh my gosh, I didn't talk about this either. Okay, gravitational wave. Einstein said that space and time are together called space-time, and they move according to gravitational, or they bend and stretch in the presence of matter. And if you move the matter or you change the matter somehow, explosions or things happen in space. We actually know, in fact, now that black holes merge and collide and make a new black hole. Those are the first type of gravitational waves that were detected in 2015. It's a pretty new technology. It's very exciting, super exciting. It's going to change everything, it turns out. But gravitational waves are a brand new phenomena that you need to know a little bit about that we can measure them. They are literally the vibrations of space-time. Now, the kilonova was even more cool because it is the merger of 2 neutron stars. Because they're neutron stars, when they smashed into each other, they exploded and we could see it, right? You can't see black holes collide. We're going to learn why in just a minute, maybe. Okay, but neutron stars are different. So not only did we see the gravitational waves, we saw visible evidence from it. The first time ever. And it happened in September 2017. No, August 2017. Okay, so it's a brand new kind of thing. All right, let's see. I don't know if I told you this story, so I better tell you real quick. Charles Messier was actually one of the people looking at this cloud called the Crab Nebula. And actually, he was just the first one, maybe. But then as time went on, people watched it. It grew. And so this cloud that grew, they managed to calculate the speed that it was growing, right? How fast is it going? And of course, the very first thing that they did, once they had the speed, is they tried to play the movie backwards and imagine, what if it came from one common center? How long ago would that be? And they came up with the year around 1050. And when they looked through astrology, it was astrology reports, they found that in China, the Chinese astronomers had noted a very special event, the guest star of the year 1054. And so this was a star that was so bright it could be seen during the daytime for 3 weeks and for 2 years at night. And so we actually, for the first time, said this was a star exploding, a supernova. Never knew that before. So that was the very first one, kind of exciting. How is matter lost on a giant or supergiant stage? I'm jumping right there. So you're big, you're huge. Every pulse of energy makes a shell of material get away from you. That's the idea. Very simple. Don't go complicated. But you're getting blown away because the amount of gravity is small. And so you end up blowing away. 80% of your mass is typical. That's the right answer about that. How do planetary nebula form? I gave you the first part, right? A giant pulses energy, it pulses material in shells away from its center. And then when there's nothing left, your core runs out of fuel, it collapses and forms a white dwarf. The white dwarf shines with ultraviolet light that energizes the gases and makes them glow for about 500 years. Not spherically symmetric comes from swallowing planets or having a companion, which makes you kind of a little bit different. Okay, and I think I went through this already. And right now, the smallest mass black hole is the one left behind from the kilonova. By the way, just so you know, at the time that it happened, we saw the event, but it was we couldn't tell at first what was left behind. It was either going to be the most massive neutron star we'd ever seen, or the smallest mass black hole we'd ever seen. And we now know, we think very strongly that it's a black hole. It has the features of a black hole. So that's the smallest mass black hole we've ever seen, okay? And it could be smaller, but that's the one right now. Why don't we see a lot of pulsars? Okay, so why don't we see a lot of pulsars? Anybody? Pretty simple idea, because they're not going, their jets don't go in our direction. If they don't go in our direction, we never see them. So that's the reality. We only see a small fraction of them. What happened on August 17th? And the answer is kilonova. You should watch the video and definitely take that quiz. But what happened is we saw a gravitational wave and we saw visible light. Chandrasekhar limit. Okay, I got all that, I think. Okay, final chapter. Okay, if you need to leave, you need to leave, but I'm going to keep going. Let's finish it up. Yeah. I'm going to come up there. I can't hear you. Gravitational waves and kilonova was the last word. So the kilonova was the merger of two neutron stars on August 17th, 2017. So you should watch that video. There's a 5-minute video that explains the interesting things about that. I mean, I'd watch it right now, but I think I should review the other stuff. Okay? All right, so this is new too. So, okay, what do you got to do? Okay, it's going to be the quick version of it. Wow, super quick. How do I do this? I'm going to tell you the essential ingredients, okay? There's obviously more because I'm going to take longer than this to explain it when I teach you on Tuesday. So anyways, we'll do our best. So Einstein came up with, well, first of all, a black hole. Let's start with that. What is a black hole? Why don't we try that? What is a black hole? A black hole is more than 2.7 solar masses that are smooshed together so tightly that light cannot escape from them. And so the concept that we're going to come up with in a few minutes, maybe I'll just start with this. Let me start with this. What is the size of a black hole, right? Let me start with that. That's actually a pretty nice and simple thing to come up with. And it's something you need to know anyways, okay? So the concept of escape velocity, what does that mean, escape velocity? The velocity needed to get away, right? So for the Earth, the escape velocity is about 11 kilometers per second. If you're on a rocket and you go 11 kilometers per second, you can get away. If you go any slower, then eventually going to crash back down to Earth, okay? Or you can go into orbit. You can do that too, sorry. But if you want to get all the way away, you have to go at least, this doesn't stick, okay. You got to go the escape velocity. So escape velocity is a principle that you understand, right? The escape velocity, the speed needed to get away. So you take like the Earth, right? You're in a rocket. And the velocity you need to get away. Did you guys sign in? You signed, right? Sign the attendance? Okay, have a good day. Okay, the velocity needed to get away is about, for the Earth, it's 11 kilometers per second. Okay, if you go 8 or 9 or 10, then you're going to end up falling back down, right? If you go anything less than 11, then you can't get away, right? So the escape velocity is how fast you need to go to get away. And it turns out that there's a limit to how fast you can go. And we're about to get to that in the theory of relativity. And the limit is, who knows the limit? The fastest escape, fastest speed. The fastest speed is the speed of light. C, okay? You can't go faster than C. So a black hole is actually I don't want to talk about it right now, but I have to say it, I guess, is a point where all the matter is a point, mathematical point, I feel ill. Okay, I'm not going to talk. It's called a singularity. It's got to be wrong. Got to be wrong. Gross. Infinitely dense. Zero volume. This is not right. But anyways, I don't know what's wrong with it. I have an idea, but I don't know. But anyways, that's where all the mass is located. And it turns out that because you've got all that mass, the gravity is very profound, right? If you're nearby, there is a mathematical place, which is the boundary, if you want. It's not really a physical boundary at all. It's a mathematical place called the event horizon. This is a word you need to know. The event horizon. It's also called the Schwarzschild radius. Schwarzschild radius. I don't write that word very often. Okay. And what is it? It's the distance at which the escape velocity is the speed of light. So the event horizon, same thing as the Schwarzschild radius. The escape velocity is the speed of light. The escape velocity, let me put this, VE, right, for escape velocity, equals C. The escape velocity is the speed of light. And you can't go faster than the speed of light. Not even light could go faster than the speed of light. So if you're a light wave and you're coming, if you go inside this radius, you can't get out again. You're done. Right? Light is trapped by gravity, by the black hole. So once the light is inside this boundary, it can't get out because the escape velocity is the speed of light. So anything that goes within this is gone forever, cannot ever re-enter the rest of the universe. Okay, what does that mean? Where does it go? Well, presumably it gets squished down into the singularity, but we don't know. Right? There are other ideas, by the way. But we don't want to go sci-fi on that, right? Do we need to know that mass is a singularity? What do you need?
Like the center of black hole?
Yeah, the center of black hole is called the singularity, where all the mass is located, yeah. You do need to know that, yeah. I think it's coming up. Actually, I don't know if it is. I don't see it on the list. Is it on the next page? This must be on the next page.
Yeah.
Okay, good. I was like, you got to know that. How come I'm not macking? Oh, there we go. Okay. Okay, so you can see singularity, event horizon. Okay, so you need to know those words too. This is the next page. Okay, did you not get it? Oh yeah, there, yeah. Okay, so now, if you want to understand what's going on, you have to understand two types of relativity. They're both relativity, but there are two different types of relativity. One is called special relativity, and the other is called general relativity. Special and general relativity. So there's two kinds of relativity. How can I do this so fast? How can I do this? Okay, figure it out. You got this. You got a PhD. You can do it. I don't know. I'm a little unsure what I should do here. There's so much material. Okay. Okay, you know what? I have to be more efficient than the slides. So the word special theory of relativity, we'll start with that one. Things going fast. That's what it's about. Things going fast, right? Special theory of relativity. Things going fast. In fact, the best things would be things near the speed of light, right? So again, I'm not going to waste your time. I want to give you the essence, and we don't do a lot of calculations in this class. So you might be like, why are you telling us anything about calculation? Because I want to get your appetite whet. Maybe a few of you will join me. Maybe you'll want to learn more later. I just can't use the slides. They're too small. They're too inefficient. We're going to be super efficient. Okay, so number one, I'm going to tell you that Einstein came up with this theory that absolutely blew everybody away, and he did not get the Nobel Prize for this, just so you know, because they didn't believe it was real, right? It took a few years before they found the real, we could do the experiments to prove that it's right, but it's right, okay? It's really right. So just so you know, he didn't get a Nobel Prize for something that is absolutely one of his biggest creations, okay? So what is the special theory of relativity? Things going fast, near the speed of light. There are two postulates. You need to know them. The two postulates are the foundational concepts that provide you, if you believe in them, then you can believe in special relativity. They're not that hard to believe, by the way, but one of them is a little more difficult. So you want to know these two postulates. Postulate number one, the laws of physics are the same for all inertial reference frames. So I want you to be aware that the words are very careful. There's a lot of detail here that I'm not going to go into because you don't need it. But there is a word here that you should know, the inertial reference frame. What does it mean? If you are moving with a constant velocity, then you are said to have an inertial reference frame. You're not accelerating. So if you remember the word velocity, constant velocity means you're moving at the same speed and the same direction without changing. You're not accelerating. It doesn't apply in any other situation. Okay, do you get it? So that's number one. The laws of physics are the same. I can exhibit this, I'll display, give you an example. If I drop keys, right, what happens? They fall into my hand. It's pretty boring. But what's really exciting, and if you've never tried this, you've got to try it the next time you go onto a plane, traveling 500, 600 miles an hour, you're sitting in your seat, level, constant speed, right? And drop the keys again. And guess what? They fall straight into your hand. It's as if you were standing still. Raise your hand, you've had that experience. You're on a plane, you're like, are we moving? And you know you're moving because you can look out the window. But if you didn't look out the window, or maybe on a train, it's a little better on a train sometimes, you just can't feel that you're moving. You're like, are we moving? And you're in fact moving, right? It's so smooth though, you couldn't sense it. So you can't feel the speed, you feel the acceleration, right? And anyways, so the laws of physics are the same. Are you good? Number one, laws of physics are the same. So we don't have to learn different physical laws, they're the same. Is that okay? Kind of makes sense. I like that one a lot. But I also think this one is kind of cool too. Number two, if you measure the speed of light, you will always measure the same speed. The speed of light is the same for all observers. Okay. Now this one's a little weird. This one's a little weird. Actually, I'll tell you Einstein's story. He said that what he was imagined, he had a thought experiment. He said, imagine I'm on a train and I'm looking in the mirror at my reflection, and then the train begins to go faster and faster, and the train goes the speed of light. Can I see my reflection anymore in the mirror? if the train is moving forward at the speed of light, can the light leave my face and hit the mirror and bounce back into my eye? Would I be able to see my reflection? Now, how many people say no, there's no way you could see his reflection? How many people say yes, you would see your reflection? Okay. And how many people say that the normal laws of physics would be that you can see your reflection, therefore you can see your reflection? So if you go with the first one, the answer is you see your reflection, and that's in fact what he had to go with, right? So it doesn't matter how fast you're going, you always see your reflection as if you weren't moving. But that's really weird. I know you can't see it quite yet. But what it tells me is that time is not absolute. I'm going to just pause because that should screw you up a little bit. Time is not absolute. It means that the amount of time something takes depends on how fast you're moving relative to the observer. There is no absolute clock that the universe follows. It does not exist. So we have a clock on Earth, and people living on, or beings on another planet, moving relative to us, have a different clock. And if we try to talk to each other, we're going to find out that our clocks don't tick at the same rate. You should be freaked out right now, no? Okay, it's pretty disturbing, but it's something you have to let go of if you're going to believe in special relativity. So I'd like to just actually the way I'm going to do this very efficiently is I'm going to show you a friend of mine's animation, and then I'm going to ask you to understand that you have to believe, if you believe these two postulates, these are the two postulates. This is all the foundational ideas he needed, and a little bit of math. And he showed that time is not absolute, okay? Okay, so we are going to, I know it's going to be weird. Okay, flash, SBCC, flash, physics. Thank you, Don Ion. There we go. Oh, what? Does it work? There it goes, okay. Okay, so the concept of simultaneous, actually, you know, this is the wrong one. Maybe start with this. This is okay. Let's start off with something. What's simultaneous mean? Two events are simultaneous. What does it mean? Same time, same time. Like there's two flashes, they're simultaneous. How do you know that they're simultaneous? Well, you can stand right in the middle and then look for the flashes of light. And if they come at the same moment, because you're right in the middle, they must have left at the same moment. Does that make sense? They were simultaneous. Well, anyways, don't worry about it too much. So these are called simultaneous, right? But how about if a rocket ship comes by? Will the rocket ship see those events as simultaneous? And at the moment that the middle of the rocket gets to the middle of the station, the signals get blasted out, right? And what you want to understand is what was simultaneous in one frame of reference cannot be in any other frame of reference. So if you analyze it carefully, watch carefully, at the moment that the data recorder goes right in the middle, what's going to happen? The flashes are going to start, right? Now here they go. The flashes go, right? And then what? The flashes go, and the first one, the one that's in the front, hits the middle of the rocket first. So according to the person on the rocket, that flash happened first. It did not happen at the same time. That flash in the front happened first, right? The events are not in the same order, okay? And then the person on the station sees both of them simultaneous, and then the last one, finally, the second flash happens, right? So they are definitely not together. They're not simultaneous, right? Okay, and now this is the one, time dilation. Keep that, play that. Okay, so we're gonna make a simple clock, which is gonna bounce a laser beam off of a ceiling back down onto a detector, and we're gonna measure the length of time it takes to make this pulse, right? And the experiment is gonna take place on a moving car. We don't do math. If you want to do math, take the astrophysics class, we do the math. It's a really simple calculation. But the time measured where the experiment is located is called the proper time. So you should write that down. The time measured by the person who's performing the experiment is called the proper time. So the idea is Einstein imagined, take this experiment, put it on a train. Yeah, the time measured where the experiment is being performed is called the proper time. Oh, that wasn't your question? Okay, proper time. The time measured by the person where the experiment is located. Now, if I take this and move it, the interesting thing is that the light still hits the mirror and bounces back and touches the ground. But in order to do that, is the light going to travel vertically up? And the answer is, well, by the time it gets to the roof, the mirror is not there anymore. It'll be over here. And so the light, if you watch the light from the side of the road or the side of from the earth as the rocket goes past, you'll see that the light is not vertical. It's pointed at an angle. Has to go at an angle. Are you guys getting that? Otherwise, it won't hit the mirror and it won't bounce back down. So you will see different things. Which one is correct? Which version is correct? What happened? They're both correct, right? They're based on your frame of reference, okay? Okay. So, in fact, this is what you see when you watch the rocket go by. That's what you see on the rocket, on the right-hand side. And the left, you're seeing what you see as you watch the rocket go past. Everybody okay? You see different things. That make sense? There's another analogy if you want. If I throw my keys in the air, right? They just go vertically up in the air. But if I walk forward and throw them up, did you see the path that they take? They take a parabolic trajectory, it's called. Which one is correct? See, from my point of view, they went straight up and straight down. But from your point of view, when you watched me walking, you saw the parabolic trajectory. We both saw what we saw, right? What we saw is correct, but it's based on our frame of reference, right? So what you see here is different. I'm trying to get across this point that we see the light traveling in different ways. Are you okay with that? I'm letting it sit in for a second. You just told me you're okay with that? In which version of the problem does light travel a greater distance? Over here, over here. So straight up and straight down is a greater distance, or this one at an angle is a greater distance? Which one's a greater distance? So they both go up the same distance, but this one went forward as well. So this light traveled a greater distance, which means it took more time. You literally measure more time passing because in order for the light to travel that far, if light travels at the same speed, it has to take more time for you. So this is called time dilation. That's the term. Time dilation. I know, freaky, right? Don't get upset. It's just life. You know, what are you going to do? You just never knew that it was right, but it's in fact the correct answer. And then the other thing is, I think I can't look at the slides anymore, but too bad. There's an equation. You don't need all that. But you can derive that. If you take the astrophysics class, we derive that. And we have fun doing it. If you don't think that's fun, then don't take the class. It's probably not for you, but it's okay, you know. But let me just show you something important, right? So there are 3 effects that you want to know about, and then we're almost done. Thank you for holding on. Okay, this is super speedy, right? The 3 effects of relativity for special relativity, the 3 primary effects. So one is called time dilation. So the length of time you spend watching a rocket go by will be longer than the time spent on the rocket. So the time you spend will be multiplied by this factor called gamma. I know this is not a math class, but please draw that factor. It looks like a Y, but it's got a funny little loop there. It's called gamma. Gamma. Called the Lorentz factor. And then T0 is going to be my proper time. So on the rocket, I measure this time. I measure more time if I stand and watch the rocket go by. The next term is length contraction. Maybe I should finish this one. Should I finish this? Maybe I should just keep, let me finish this. Let me keep going. Okay, so what's gamma? Gamma is a factor, a mathematical factor, 1 over the square root of 1 minus v squared over c squared. So we don't do calculations in here, so don't worry. But I want you to understand something about it. And in the slides I show you on Tuesday, you'll see it. The faster you go, the larger this number becomes. But there's a problem. As you get close to the speed of light, what would this factor become? C over C would be 1. What's 1 minus 1? 0. This becomes infinity. Right? That's a problem. Actually, anytime I get infinity, I know I screwed up. Okay, infinities are wrong. I don't like infinities, but the faster you go, the larger the gamma becomes. It turns out it's not that hard to do. What we'll usually have to do is put in something like this. V equals 0.5 C, like that. What does that mean? How fast are you going? Half the speed of light. That's it. It's only good when you're moving near the speed of light, right? So if you do this, something interesting happens. What happens to this factor, V squared over C squared? You do 0.5 C squared over C squared. What happens? What do you square? The 0.5 or the C or both of them? You got to do both, right? So you get 0.5 squared C squared over C squared. What happens to the C squareds? They cancel out. That's the cool part. And so if I did this calculation, it would be 1 over the square root of 1 minus 0.25. 0.5 times 0.5. It's something that's not that hard to do. You don't have to know this, whatever. Just trying to show you, it's not that hard to do. So when you do this calculation, you get a value, a number. In this case, it's just going to be a tiny bit over 1, really a little bit over 1. But as you go faster and faster, this factor becomes larger. So let's say that I told you that the gamma factor was 10. Let's just say I just give that to you. And there's a story that you want to learn called the twin paradox, where a pair of twin sisters are born, right? And one is the astronaut. She's going to get on a rocket, and she's going to move near the speed of light so that the gamma factor is 10. And she's going to take off, and she's going to take a 1-year journey away from the Earth and back. She's going to be 1 year older. How much older will her twin sister be? So she measures 1 year passing on the rocket, but back on Earth, we measure 10 years passing. Her twin is no longer the same age as her. I know, you're like, you can't believe me. I'll show you proof on Tuesday, okay? I have a video where they did the experiment, okay? Are you guys okay? Okay, so factor number 1, time. I know you're not okay, but that's okay. We don't have time for this, okay. So factor number 1, time dilation. The time that you experience watching the rocket go past is longer than the time spent on the rocket. Second effect, length contraction. So even distances are not going to appear the same. So the length that you see is the proper length divided by gamma. Now, if you are on the Earth, here's Earth, and you measure the distance to a star, right? Then I'm going to call that the proper length. That's the proper length. But if I get in a rocket and move really fast, right? What happens is I measure the distance as L. And according to this factor here, are you multiplying or dividing? You're dividing. So if the factor was 10 again, you would see the distance as 1/10 of the original distance. So the stars are getting closer. Isn't that exciting? The faster you get to the speed of light, the closer the stars will appear to be to you. And the third and final factor that you have to know about, you got this part? Called length contraction. So what you see in the rocket is shorter than the actual distance. So the actual distance for you is shorter than the distance for the people who live on Earth and don't move. Length contraction. The third and final one is called, oops, I missed erase. Okay, relativistic mass. Okay, the mass of an object is gamma times m0. What's the m0 going to be called? The proper mass or the rest mass? The rest mass. The mass of an object at rest is its rest mass. The faster you go, the greater the mass becomes. And it's all based on this gamma. So if you go too fast, what happens? If you try to go the speed of light, what happens to gamma? It becomes infinite. If you go the speed of light, if you're a piece of matter, you have infinite mass. That's a problem. If you remember, in order to make something speed up, you have to push on it with a force. The more mass you have, the harder it is to make it speed up. So what happens is, because of this relativistic mass, a mass particle, mass cannot reach the speed of light. You can't go the speed of light. That's the end of it, right? You can't go the speed of light. See you guys. Thanks for being here. All right. Time dilation, relativistic rest, mass, space-time. Okay. Okay. All right. Getting close. Okay. So I've mixed in some stuff here, but we're now down to the last theory, and this one is not mathematical. So actually, let me stay on the board. I'll just stay on the board. The next one is called general relativity. General relativity. Actually, I need to just show you at least one thing, huh? General relativity is the concept that space-time is going to be shaped by the presence of matter. So general relativity is space-time, gravity, and matter. I have in there. Okay, before I do that, let me do this. Let me show you at least one picture. So the concept is when you have matter, it bends or warps space-time, and the warping of space-time is going to change it from being flat to being highly curved, right? Space-time. Okay, so that's the idea. If you think of a sheet, right? Space-time is flat where there's no matter, but the greater the mass or the more concentrated the mass, the sharper the curvature will be, the greater the curvature will be. Now the problem is this is not right because space is not two-dimensional. Okay, so it really has to be in every direction as well. So you take the sheet and then replicate it in any possible orientation, and that would be the reality. So anyways, what I want to tell you is this radius around a black hole that we're going to talk about, black holes are spheres, not flat at all, right? They're spherical. Okay? So blah, 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 that's space-time curvature right there. The greater the mass, concentration of the mass, the more curved it is. Now, actually a really interesting thing, let's say that the yellow is the sun. And you can see that that curvature doesn't seem to go very far, but if the red is a planet, then the planets are following the sun around, they're orbiting the sun because of the force of gravity. So the curvature of space-time tells you how strong the gravity would be. And that's what it tells you. So something would happen. What if aliens came and squished the sun down into a point, a singularity? What would it become? A black hole, right? But what would happen to us? And the answer is, out where we live, the curvature of space-time wouldn't change because the mass of the sun hasn't changed. It's just the density of the sun has changed. So you created a black hole, but what that did is just made the mass more concentrated, made the curvature stronger inside, but out here it looks normal. We would continue to orbit that black hole, right? And it would be really cold because there'd be no sun, so we'd all die. But anyways, that makes sense? Okay, so the curvature is based on the total amount of mass, really, okay? Blah, 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 why am I doing that? Okay, because you got the basic idea, the curving, right? Okay, so the two things that you need to know. Okay, now it's said. All right, now I'm going to tell you the two things you need to know. There's two key ideas, and they're not mathematical, they're just ideas. What are the two things that happen that we see? And specifically, they're applied to black holes, but it could be anything. Let's put a mass here, whatever it happens to be, the Earth, a star, black hole, whatever it is. I want to tell you about, there's a general relativistic time dilation. Okay, general relativistic time dilation. And then the other thing is called gravitational redshift. Okay, let's start off with the first one. What is the time dilation effect? The clocks tick at different rates. That's what it means. Which clock is going to be faster and which clock is going to be slower? Well, you're always going to see your clock as normal. So the question is, where's the other clock? Is it closer to the mass or further from the mass? And so the answer is the strength of the gravitational field affects the ticking of the clock. The stronger the gravity, the slower the clock will tick. The slower it will appear to tick from your perspective. So stronger gravity, which means greater curvature, slower clock. Okay, so if I put a clock at the surface of the Earth, right, and I have a clock in orbit, which one will tick faster? The one in orbit, because you're further away from the gravity, right? A little bit weaker. So if you're up here and you look down, Yeah, I'm talking too much. Can you hear me again? Okay, so this is a simulation showing you what's going on, but there is, what we see is these stars are orbiting some invisible companion. There's nothing there. And when you calculate the mass of that thing, it has to be a black hole. So it's a 4.1 million times the mass of our sun, 4 million times the mass of our sun. And yeah, it's very quiet right now. Except recently it did flash with a gamma ray, actually. Did you hear me again? Did it come back? Oh, yeah, okay. My batteries are dying. Okay, so I'm actually just about at the end of the review. Let's see. Did I miss anything? I missed muon and cosmic rays. Let me tell you that one real quick. A muon is a particle that can live for just a very short amount of time. Sorry. When cosmic rays hit the upper atmosphere of the Earth, they make muons. And these muons can live a very, very short time, actually a fraction of a second. They live such a short time, none of them should make it down to the surface of the Earth. But if you go out and measure them, we measure them all the time. And the reason is because they're traveling near the speed of light. So from our point of view, they're living much longer because they have had time dilation effects taking part in their life. So they live a lot longer as a result of that. And that's one of the evidences for this. And gravitational lensing, I should show you that. Gravitational lensing, last thing, and then if anybody wants to stay, I will do the questions with you guys, but only, I'm gonna turn off the video. Gravitational lensing is the idea that if you had a beautiful galaxy, right? This is Einstein's idea. You have a galaxy, then there's a galaxy behind that original galaxy. You shouldn't be able to see that galaxy, except that gravity bends light, we know. We now know gravity bends light. And so we can see that galaxy that's behind this front galaxy because the light comes around the side and bends, and so we can see it. And Einstein said if it was perfectly lined up, you could actually see a ring all the way around another galaxy. So it's called an Einstein ring. And the most amazing thing is that the light takes different amounts of time coming from different sides of the ring. And so if you see a supernova go off on this one, they have now had a very successful prediction of how long it will take for the supernova to go off in the other one. They say within 60 days, and sure enough, in 54 days, the supernova shows up in the same position on that other galaxy. And so that we know then that the light is coming from the same source, but traveling in slightly different paths. It takes a little longer on one side, a little shorter on the other side. Okay, that's it for my review. I'm going to end the stream. And if you want the questions, anybody want the questions?